Hello, in this video we're going to consider the situation in which a submerged cylinder is approaching a wall, and in particular we are going to solve for the flow that occurs in between the cylinder and the wall. So before solving for the cylinder, for the flow around the cylinder approaching a wall, let's first draw what the situation looks like. So we do have a cylinder. I'm going to draw the cylinder roughly like this. There's a wall at the bottom here. Okay, the wall is static and our cylinder has a radius A and is moving downward with a velocity V. Okay, the separation between the cylinder and the wall at its smallest distance is D, and in general I'm going to call this distance H, and it varies with the horizontal axis, of course. And as usual, we're doing fluid dynamics, and so this is a situation where there is a fluid around. So in what follows, we're going to take into account the context of lubrication flows. So that means that we are going to make the assumption, or we're going to place ourselves in the specific case where D, which is the separation between the cylinder and the wall, where D is small compared to A being the radius of the cylinder. And what this is going to give us is a situation that is a little bit more so this is our wall, a little bit more tractable analytically. That's going to be the curvature of our cylinder, okay? And that cylinder is pushed downwards at velocity V. And you can see that I made this curvature in such a way as to indicate that the cylinder is actually gigantic compared to the size here, compared to the area that I've plotted there. And we're going to define here our axes. So this is EY in the pseudo-vertical direction, and this is EX. Okay, and 0 is going to be placed at the location where the separation is minimum between the cylinder and the wall. So first of all, let's express what H is. So H of X is, well, it's D plus a little bit more here, which we can figure out by taking this triangle. So it's D, and then it's going to be plus this distance minus this, so plus A minus, and then we just apply our usual Pythagoras theorem, A squared minus X squared. And, well, because we're zooming in here, we can make some approximations for this. In particular, we're looking at D very small compared to A, and so we're zooming in this area, and so the variations in X are going to be small compared to the size of the cylinder. Okay, so X is going to be small compared to A, right? The radius here is gigantic, and so we're just considering that area where this the displacement in X is going necessarily to be very small compared to the size of this cylinder. And what that tells us is that we can rewrite H of X in a slightly different way. We can take out A squared off this square root, so that's going to be D plus A minus A, and we have a square root of 1 minus X squared over A squared. And with X being small compared to A, that can be approximated as D plus A minus A, this is a D, 1 minus X squared over 2A squared, or in a slightly more dense form, D plus X squared over 2A. Okay, that will be the first, like a sort of first approximation for the height of fluid here as we move slightly away from 0 along the X direction. I'm going to, as an anticipation for what will follow, there's a natural scale in the vertical direction which is d, okay? This is the separation, the minimum separation between the cylinder and the wall. So I'm going to factorize this by d. This is going to help our investigation. So that's 1 plus x squared over 2ad. And you're going to understand why I'm doing this when we proceed to the non-dimensionalization of the system. Okay, so this is our preliminary work done. The first step is, as usual, to write down all the equations, boundary conditions, everything that we need to know to solve for this problem. So let's first write down the equations. So we are in the context here of lubrication flows, so we are going to be looking at low Reynolds number flows, that is to say the Stokes equation. But first of all, let me just write down the incompressibility condition. So that will be du by dx plus dv by dy equals 0. Then I've got the Stokes equation, which is mu d2u by dx squared plus d2u by dy squared equals dp by dx. And I've also got mu d2v by dx squared plus d2v by dy squared equals dp by dy. Okay, so these are my incompressibility condition and my Stokes equation. This is to be solved together with the following boundary conditions. So first of all, at y equals 0, I must have 0 velocity in the fluid, so u equals 0. And when I'm looking at y equals h, that's at the border, at the boundary with the cylinder, I must find that the velocity of the fluid through this no-slip boundary condition has to match the velocity of the boundary, that is to say minus v ey. And that's the set of boundary conditions and equations that I've got to solve here to know what the flow around this cylinder approaching a wall looks like. So, as usual, the first step in to find the solution after writing down these equations and boundary condition is the non-dimensionalization. So let's look at non-dimensionalization. As I said, there's a natural quantity that will help us non-dimensionalize our equations, which is d in the vertical direction. So I'm just going to non-dimensionalize the vertical lengths or in the y direction by d. So I'm going to write down y equals dy star. Then we need to think about what to do for the x direction, because, well, we don't have anything that tells us where how long, what are the length scales for the flow in the x direction, by just looking at the problem this way, except that we've written this equation for h here, that involves an x. And the idea here is that we will notice that h starts to be impacted, that is to say that the domain height starts to be impacted as we move in the x direction when x has changed of a magnitude that is approximately the square root of AD. For x smaller than square root of AD, this term is negligible compared to this, and therefore h equals d. Okay, so that's a very close region here, close to the center of the domain. And we're going away from this region and therefore starting to feel the curvature of the cylinder when this term here is no longer negligible compared to this term here. Okay, and that happens when x squared is of the order of magnitude of 2AD, or AD, this is just like a prefactor. In other words, when x is of the order of square root of AD. As a consequence, I'm going to write down that my non-dimensionalizing quantity in the x direction is square root of AD. And you can add the 2 or the square root of 2 if you want in front of it. This is up to you, but just for the sake of the calculation, it's going to be easier not to carry that 2 in front of it. In any case, this is a rescaling, and it's not going to change the order of magnitude of my term to have the 2 or not. It's just an order 1 quantity. And so I can just take this, which will simplify my calculation, rather than having the 2 come in. And because this is a distance, it's also nice to have d appear in front of it. And if I have d appear in front of it, what I need to do is multiply this by square root of a over d, okay, and I can define and remember that d is small compared to a, so that quantity is large. So I can write down that this is d over epsilon times x star, with epsilon being square root of d over a being a small quantity. So it's quite customary to introduce a small quantity as being epsilon. So here it's got an expression that I don't want to carry across all my calculation. It's going to be quite annoying to carry this out. So I'd rather introduce this quantity epsilon, and in mathematical parlance, whenever we see epsilon, we always think of a small quantity. So this kind of natural fits the will easily fit the mathematician's brain. So this is it for x and y. Now we have to look at the velocity and the pressure. For the velocity in the y direction, there's an obvious scale, which is the velocity at which the cylinder is pushed downwards. That's a clear one. The velocity in the x direction, so far we don't know anything, so this is going to be determined. Okay, that's to be determined. And similarly, we need to non-dimensionalize the pressure. As usual, at this stage of the reasoning, we do not know how to non-dimensionalize it. So I'm going to introduce a dummy scale here, capital P, and I'm going to have to determine it. Okay. So this is it for our non-dimensionalization. So we're going to essentially plug all this in the equations. Let me just label this one equation 1, this is going to be equation 2, and this is going to be equation 3, and determine UP, and then ultimately find out what the dominant terms are and solve for the flow. So if I plug these scalings into equation 1, what I get is u epsilon over d du star by dx star plus v over d dv star over dy star equals 0. I can multiply everything, forgot the implication sign. I can multiply everything by d, and by doing this I am getting u epsilon du star by dx star plus v dv star by dy star equals 0. And at this stage I need to decide what the scale for u is, and I've got a strong argument here, which is that I would like the flow to remain two-dimensional. So this is my part of the point of introducing this epsilon quantity. And to make this flow remain two-dimensional, I need these two terms to balance. In other words, I need u to be equal to v epsilon minus 1. Okay? So this is my first, so that determines u. So this is my first quantity that is determined. Now I need to turn to p. And to determine p, I've got two more equations that involve p, and I'm going to plug my non-dimensionalizing quantities into the Stokes equation and see what they become. So equation 2 will become mu v epsilon minus 1 epsilon squared over d squared, d2u star over dx star squared, plus mu v epsilon minus 1 over the d squared times d2u star over dy star squared. And that's equal to, so I've got my pressure gradient to the right hand side, so it's p epsilon over d dp star over dx star. That's my first equation. I can multiply everything by d2 over mu v epsilon to the minus 1, so that this term has a unit prefactor. And if I do this, then here I've got epsilon squared left, d2u star over dx star squared. I've got my unit prefactor here, so that's d2u star over dy star squared. On my right hand side, I get p d epsilon squared, that's correct, over mu v dp star over dx star. Okay, so immediately here, what we can notice is that I have viscous forces here have two terms, and one of these terms is small compared to the other one. Okay, this is an epsilon squared as a prefactor, taking out the scaling of this quantity, being small compared to this one, which has a unit prefactor. So I'm going to neglect this term for the remainder of the calculation. I can do the same thing with equation 3, and I'm going to label this equation equation 4. I can do the same thing then with equation 3. And that gives me mu v epsilon squared over d squared d2v star over dx star squared plus mu v over d squared d2v star over dy star squared. And that's going to be equal to my pressure gradient in the y direction, which is p over d dp star over dy star. Similarly to before, I'm multiplying everything by d squared over mu v, and that gives me epsilon squared d2v star over dx star squared plus d2v star over dy star squared. And on the right hand side, what I'm getting here is pd over mu v, pd over mu v, that's right, dp star over dy star. And much like we did for equation 2, that term is small compared to this one, so my viscous forces are dominated by the y derivative of my velocity, and I can take this out. I'm labeling this equation equation 5. So now we need to determine the scale for p, and we do have two equations. So let's have a look at what these equations give us. So equation 4, if I want to keep the balance between friction or dissipation and my pressure gradient, then I need p to be equal to mu v over d epsilon squared. And similarly, if I look at the same, if I make the same reasoning with equation 5, I need p to be scaling like mu v over d, mu v over d. So I've got two different scales for the pressure. They are the same with the factor epsilon squared difference between them. So this is actually a very large scale. You have a small coefficient in the denominator, so that is a very large scale, and this is an order 1 quantity, let's say. We can choose this one, say that p scales like this, but then the scaling will not include large pressures that come from equation 4. So rather than doing this, we have to choose, to not lose in generality, we have to choose the larger of the two scalings, which is mu v over d epsilon squared. Saying that the pressure is large means that the small pressures that are going to be coming into equation 5 are still included in the calculation. And so that gives us the scaling for the pressure. So based on this, we've found out what all these scalings are. So we'll just write down a quick summary of our non-dimensionalization and what the equations become. So we had x that was non-dimensionalized using d over epsilon, then we have x star, y was non-dimensionalized by d, then we have u that is coming, that was determined, this is v epsilon to the minus 1, u star, v is non-dimensionalized using v of course, and then p, which we've just determined, is mu v over d epsilon squared times p star. Okay. At this stage, there is an interesting thing to look at, which is what actually we should have done that earlier. What h becomes, right, or this expression rather. So remember that h is a height, so it's quantity in the y direction. So we need to non-dimensionalize it using d, which is the reason why I took this d out here. So if we want to non-dimensionalize h, so h star equals then, h being h star d. So we've got here, we're left with 1 plus, and we need to non-dimensionalize x squared. So that's going to be d squared over epsilon squared times x star squared over 2ad. These are coefficients, so they don't need to be non-dimensionalized. Based on the definition of epsilon, which is given here, what we are getting is a nice simplification, because h star becomes 1 plus 1/2 of x star squared. It's a very nice and simple expression for h star. And interestingly, it follows from this that if I take the spatial derivative dh star by dx star, well, I just get x star. Okay, so these are so these nice simplifications, the fact that these quantities write so nicely is a consequence of the fact that the non-dimensionalizing quantity here, the non-dimensionalizing quantities here are well chosen. That makes our problem much more easy to manage. So this is our non-dimensionalization. So the equations, remember that we have the incompressibility condition. We kept the balance at this stage, so both terms will remain. So that's du star by dx star plus dv star by dy star equals 0. Coming out from replacing u here by v epsilon minus 1. Then for equation 2, that's our equation on x, we ended up with equation 4 by replacing the p by the scaling that we found there. That term becomes 1. And so equation 2 becomes d2u star by dy star squared equals dp star by dy star. And lastly, equation 3, which was simplified into equation 5, can be simplified even further by replacing the scaling for the pressure P by this quantity here. And what we see is that there's a term 1 over epsilon squared. What happens when this term comes in is that it breaks the balance in this equation and makes the pressure gradient much stronger by a factor 1 over epsilon squared compared to this viscous term. As a result, from equation 5, the only term that remains is dp star by dy star, and it's equal to 0. So these are equations. These are our equations here. So I'll label this one at 6, 7, and 8. And last but not least, the boundary conditions. So at y star equals 0, we should have u star and v star to be identically 0. And at y star equals h star, I should have u star equals 0 and v star equals minus 1 because of the minus sign here. And so now, based on this reduced system, we can now try and find a solution. So first of all, we can look at equation 8, and equation 8 directly tells us that the pressure doesn't depend on y, and crucially, that means that the pressure only depends on x, which is nice because this was an x. Okay, I made a mistake there. So this is an x. Of course, it's the x component of the Stokes equation. So now that we have established that P only depends on x, it does not depend on y, we can integrate equation 7 with respect to y and find the velocity. So let's do that. So equation 7 gives us that u star, so it's an equation, second order equation with dp dx on the right hand side. So u star is going to be equal to 1/2 of dp star by dx star y star squared. There will be a constant of integration here that may or may not depend on x times y star, and then another constant of integration that may or may not depend on x as well. So that's our velocity. We can determine some of these constants by applying the boundary conditions. In particular, if we take the boundary condition at y equals 0, we have that u had to vanish. What that means is directly that k2 is 0. So that makes a very nice simplification. And the second boundary condition was at y star equals h star. And at this point, the velocity also had to vanish. Remember, we're talking here about the velocity in the x direction, and the cylinder is only moving in the vertical direction. So this leads to, well, the determination of k1. K1 is thus minus 1/2 of dp star by dx star h star. There's a minus. And well, based on these determinations, we can write down that the velocity u star is 1/2 of dp star by dx star, factorizing by this, and I've got y star squared minus y star h star. And that gives us the velocity of the fluid in the horizontal direction, except that we still have this pressure gradient that is not determined, and we need to solve for it. Well, so to solve for the pressure gradient, we have no choice but look at what conditions, what information we haven't used, and turns out the only piece of information that we haven't used are the equation 6 and the boundary conditions for the velocity in the vertical direction. So we'll use equation 6 first of all to express v. So 6 gives us that dv star by dy star equals minus du star by dx star. That means that it is minus 1/2 of d2p star by dx star squared times y star squared minus h star y star, then plus 1/2 of dp star by dx star, dh star by dx star, y star. Well, based on this, we can then integrate v with respect dv by dy by integrating this with respect to y, and we're going to use boundaries of integrations to be 0 and y star. 0 is going to make us use this boundary condition. Remember, the velocity vanishes at 0. And therefore what we can write here is that v star at y star is the integral of this with respect to y star from 0 to from 0 to y star. And so let's integrate this. So that will give us minus 1/6 of d2p star by dx star squared y star cubed plus 1/4 of d2p star by dx star squared h star y star squared, and that term here, that becomes 1/4 dp star by dx star dh star by dx star y star squared. So that's our velocity in the y direction. The last piece of information that we haven't used now is the fact that this velocity is equal to -1 at the top, at the boundary with the cylinder. So let's write this up. So the boundary condition, the next boundary condition states that at y star equals h star, we have v star equals -1, and therefore -1 equals, so that's going to be h cubed, there's h cubed here as well, 1/4 minus 1/6, that's 1/12, so that's 1/12 of d2p star by dx star squared h star cubed, and then I've got that term, so this is 1/4 dp star by dx star dh star by dx star h star squared. Okay, and I can multiply everything by 12, and I'm going to work with this on the left hand side. And what I can notice here is that this thing comes from differentiating with respect to x star dp dx h cubed, right? So let's just write this down. So if I differentiate by dx star, if I differentiate dp star by dx star h star cubed, so I would get d2 p star by dx star squared h star cubed, which is this guy, modulo 1/12. And then I'm going to have times 3 h star squared dp star dx star dh star dx star. This is this term, modulo 1/12. So I'm correct. And that's minus 12. Multiplying this guy by 12. Okay, so we have that equation, and this equation is important. It's called the Reynolds Equation. It's different for any different flows, and it typically relates the height of fluid that you have to a pressure gradient. So according to the configuration that you have, you might have a different expression for the Reynolds equation, but this is this equation that allows us to eventually solve for, to determine all the quantities in the flow. So let's solve it. So integrating with respect to x, we get that dp star by dx star is minus 12 x star over h star cubed, and then I've got a constant of integration k3 over h star cubed. Okay, and then we think that we've assessed the whole problem. We think that we've applied all the conditions, but we still have a constant of integration left, k3. So at this stage we need to step back a bit and think about the problem. What is this pressure gradient, and what is the problem that we're trying to solve? And how do we get this term to play, right? So we get this term to play, we can isolate this term by setting x star equals 0, for instance. And therefore the pressure gradient will be equal to k3 over h star cubed. And at x equals 0, we're right in the middle here. Okay, it's an axis of symmetry. And what dp by dx is, it's a forcing term, right? If you think about the Navier-Stokes equation, or if you think of this equation, it's the right-hand side that forces the flow, right? So because our configuration is symmetric with respect to this axis, the x equals 0 axis, then there has to be a zero net force in the x direction at this point. And therefore the pressure gradient has to vanish at this point. All right? So what we get from this is that using a symmetry argument, which I just expressed, dp star by dx star at x star equals 0 has to be equal to 0. And the net consequence of this is that K3 has to be equal to 0. Okay, so as a result from this, we get that dp star over dx star is minus 12 x star over h star cubed. And therefore we can replace this in the equation for u to determine the fully expressed horizontal velocity in this problem. And it is minus 6h x star over h star cubed y star squared minus y star h star. And if you want at this stage, you can replace h star by this expression here, or you can reconvert these quantities into dimensional quantities. I'm not going to do this to not complicate the expressions. But you can see that here we have determined the velocity in the horizontal direction using both with its dependency with respect to the y direction, but also with the x direction. And some of the x direction is also hidden in his h stars. From this, one can continue and determine the velocity, the vertical velocity here, by replacing effectively here dh star by dx star is just x star, as we've determined a few moments ago here. We now have dp star by dx. We only need to differentiate p star again with respect to x star, which can be done very trivially from this expression, and plug this all back into the expression for v star to determine the velocity in the vertical direction. We can also continue and determine the pressure by integrating this forward, and so on and so forth. I just wanted to bring this problem to a point where it's essentially cracked, and the other quantities just follow, and this is what I've done in this video. This concludes this video on the flow around a cylinder approaching a wall.